Hi Algebra 2 students, this is Mrs. Richart. Today we're going to talk about the quadratic formula, but this time we're going to have answers that look a little bit different than yesterday. So for example, if I put x squared plus 7x plus 11 into Desmos, this is the graph I would get. And so I want you to see that these x-intercepts I've clicked on in Desmos, and this is what I'm given. So take a second to think about what you notice about these x-intercepts. You might notice that these are decimal answers and they're not decimals that we recognize. So if I want to find the exact solution to a quadratic equation, we can use the quadratic formula. When we factor and solve for our roots for quadratic equations, we can only factor when we have fraction answers or integer values. The quadratic formula can be used for all types of answers. That brings us to the difference between rational and irrational numbers. A rational number is a number that can be written as a ratio or fraction of two integers, or a terminating or repeating decimal. Some examples of this are 2, -5, a ratio of two numbers, so 1/2, 7/10. A terminating decimal is a decimal that ends, so 0.125, that's a rational number, or a repeating decimal, so 0.3 repeating, -0.7 repeating, things like that. On the other hand, an irrational number is a number that cannot be written as a ratio of two integers. It's a non-repeating or a never-ending decimal, so you cannot write it as a fraction. Some of the most famous examples of irrational numbers include pi. So we have 3.14159, etc., and it never ends and there's no repeating pattern. Another example is the number e, and if you type that into your calculator, you'll see that it's a never-ending non-repeating decimal. Another example is square root of 2. Square root of 2 we cannot write as a fraction, and it's a never-ending, non-repeating decimal. There's no pattern to it. Or negative square root of 7, for example. So the quadratic formula can help us get rational and irrational solutions. If we want to simplify these radicals completely, for an example, the square root of 24 is not a perfect square. So first, I'm going to write 24 and list the factors. The factors of 24 include 1 times 24, 2 times 12, 3 times 8, and 4 times 6. Because I want to simplify this square root, I want to choose the largest perfect square I see. So I see that 4 is a perfect square. I can rewrite the square root of 24 into the square root of 4 times 6 because 4 and 6 multiply to get 24. This is the same thing as the square root of 4 times the square root of 6. So I notice that the square root of 4 is 2. And the square root of 6, I don't know what that is, so I just leave that underneath the square root. 2 square root of 6 is the simplified version of square root of 24. If I take square root of 32 and I try to find the factors of 32, I have 1 times 32, 2 times 16, and 4 times 8. I see two perfect squares, 4 and 16. Because we want to simplify completely, you want to choose the largest perfect square. So I'm going to choose the pair 2 and 16. This simplifies. Square root of 32 is the same thing as the square root of 2 times 16, which we can write as square root of 16 times square root of 2. I know the square root of 16 is 4. However, I don't know the square root of 2, so I leave that under the radical. Square root of 32 simplifies down to 4 square root of 2. Lastly, if we take 50 and we write the factors of 50, we have 1 times 50, 2 times 25, and 5 times 10. I notice that I have a perfect square of 25. So I'm going to rewrite this as the square root of 25 times 2. That is the same as the square root of 25 times the square root of 2. I know the square root of 25 is 5, so I can pull that out. However, I don't know the square root of 2, so it stays underneath. Square root of 50 simplifies to 5 square root of 2. Let's go back to the example that we used for Desmos on the first slide. We have x squared plus 7x plus 11. When we want to find the x-intercepts, we set it equal to 0 because that is the line y equals 0, the x-axis. We want to know when we cross that 0 line. It's already in descending order for the degree, x squared plus 7x plus 11. So now we can go ahead and identify our a, b, and c. My a is 1, my b is 7, and my c is 11. The quadratic formula is down in the bottom right-hand corner, so if we go ahead and start trying to find the zeros, we have x equals opposite b, so the opposite of 7 is negative 7, plus or minus the square root of b squared minus 4ac, all divided by 2a. The most important thing to do first is to simplify what's underneath the square root. So let's go ahead and do that. So this will equal negative 7 plus or minus 7 squared is 49, and 4 times 1 times 11 is 44. So we have 49 minus 44, which will give us a 5. So we have negative 7 plus or minus the square root of 5 divided by 2. Because I don't know the square root of 5 and I can't simplify it anymore, it's a prime number, 1 times 5. That is our answer. So we can break that up if we wanted to see both of the solutions to negative 7 plus square root of 5 divided by 2 and negative 7 minus square root of 5 divided by 2. If you type both of those into the calculator, you would get negative 4.618 and negative 2.382 with lots of decimals after that. So these are the exact solutions. Let's try one more. So we have 2x squared minus 10x equals negative 5. Notice that this is not set equal to 0, so we have to move this negative 5 over. We can move it over by just adding it to the other side. So if I rewrite this, I have 2x squared minus 10x plus 5 equals 0. Now I can go ahead and identify my a, b, and c. A is 2, b is negative 10, notice the sign goes with it, and c is a positive 5. If I go ahead and do the quadratic formula, x equals opposite b, opposite of negative 10 is positive 10, plus or minus the square root of b squared minus 4ac, all divided by 2a. Once again, the most important thing to do is to simplify what's under the square root. So we have 10 plus or minus the square root. Negative 10 squared is 100, and 4 times 2 times 5 is 40. So we have 100 minus 40, which will give us the square root of 60, divided by 4. Now we have to look at the square root of 60 and simplify it. If we look at 60, I know I can say 1 times 60, 2 times 15, 3 times 20, 4 times 15, and 5 times 12. So if we look at that, I see that I have a 4 times 15, and 4 is a perfect square. 15 can't be broken down to anything else. So if we continue on, we have 10 plus or minus the square root of 4 times 15, all divided by 4. I know that the square root of 4 is 2, so I can pull that out. So I'm left with 10 plus or minus the square root of 4 is 2, square root of 15, over 4. The square root of 15 is 1 times 15 or 3 times 5, and there's no perfect squares, so we're done simplifying. The only thing that we can do next is to notice that 10, 2, and 4 all have a 2 in them. So if we divide each term by 2, and we can only do this because all of the terms have a 2 in it. 10 divided by 2 is 5, plus or minus 2 divided by 2 is 1, square root of 15, over 4 divided by 2 is 2. 5 plus or minus square root of 15 divided by 2. These are our two solutions. 5 plus square root of 15 over 2 and 5 minus square root of 15 over 2. Thanks for listening.